Good morning. My name is Steven Threlfo. I'm a biomed and I come from Newcastle, New South Wales, Australia. What I'm going to do is give you a brief overview of the Boyles anaesthetic machine and show some of the steps necessary in order to make sure that it is safe to use, and then moving on and how to test the patient circuit as well. The first thing we would do with a machine is ascertain that we have the correct gas regulators for it. We're going to be working with cylinder supplies, so we would first inspect the regulator. The primary things to look for are, does it have a high pressure seal affixed to the cylinder regulator? And also, every medical gas regulator must have 2 pins here. In various parts of the world, for various reasons, these may have been removed. These are the primary safety mechanism by which this will only adapt to a particular cylinder. At the other end of the regulator is, in this case, a diameter indexed sleeve system, and that's where our output from the regulator is connected to the machine. The other thing about regulators is that they have the facility with an Allen key to adjust pressure, and if needed, we may have to adjust pressure. It's a very simple system of basically turn the Allen key clockwise, it increases pressure, and to lower pressure, turning it the opposite direction. All regulators have a locking handle on them, and that should be fairly free flowing. So we will connect those up, but prior to doing that, I'll go through the machine itself. On here, we have 3 pressure gauges. This machine is configured for oxygen, air, and nitrous oxide. We're only going to be using, for this demonstration, oxygen and nitrous oxide. The gases pass through a safety system within the body of the machine, which we're going to check. They are blended by admitting flow through these tubes here, and these are calibrated in this case, mils and litres. So we can go from very low flow to quite high flows, in this case maximum of 10 litres per minute. The gases then pass through these tubes onto what we call the back bar of the machine. On the back bar, we have a vaporiser. Most vaporisers are detachable, easily detachable, and they fit onto this mounting system here. The mounting system has seals on it, which we have to verify are in good condition, and also some sealing valves here. This machine is a little unusual in that it only has 1. Most machines would have 2, in some cases 3 positions whereby vaporisers can be attached. So we're going to check. Part of our checking is the quality of these seals. The gas then passes through the back bar and works its way down to this outlet here, called the common gas outlet. All common gas outlets on machines have a standard 22mm taper on the outside and a 15mm taper on the inside. Normally, this is then connected through to the breathing unit, and as we can see on this machine, that has not yet been done. So we will test the machine function in two steps essentially. We will work through our gas supplies up through the machine and out to here, making sure that we don't have any leaks and that our gas supplies are being provided at the correct pressure. We will then move on and connect up the breathing system. It's it's a logical way to do that, and all we really need for test equipment is this simple apparatus. All it is a pressure gauge from a standard blood pressure sphygmomanometer set with a 22mm male connection on the end of it and just a piece of oxygen hose. We then have a 22mm to 22mm female fitting that goes over that. With this arrangement here, we can make attachments to anything on the breathing system of a standard anaesthetic machine. So we will commence. First thing we need to do is hook our regulators up. So I'll bring them across. In this case, we've got oxygen and nitrous oxide. We'll put the regulators on. It's marked oxygen, so this will go on this cylinder. And the nitrous one, checking it, seal, 2 pins. Okay, we've got both our regulators attached. We'll then find our hoses. A quick inspection to check that the seals inside these hand wheel attachments are in place, and both of them are, and they look to be in reasonable mechanical condition. Now, the first thing I want to do is turn on oxygen so that we check the oxygen side of our system. I'll just move this away so we can see the front of the machine. In the centre here is this little, what we would call a winker. You'll see there that it's red. Normally, when we turn on oxygen, we would expect that to change to green. That's a visual indication that we have oxygen connected. And also, we will see the pipeline pressure indicator here, because we're effectively delivering it via a pipeline connection from a cylinder. We will see that pressure gauge rise. So we'll turn it on. Hear that noise? That is the oxygen failure alarm. But what's unusual is that we have this green indicator coming up and the failure alarm on. And I can see here that there's a reason for that. The oxygen supply pressure is actually low. As I mentioned earlier, we can do something about that by adjusting our regulator. Simply the Allen key is put in, and then looking at this gauge here, so what we're doing now is we're increasing our pressure towards 400 kPa. So that's showing us 4 on the, That's a good sign. The alarm has stopped. Low pressure alarm. And we're heading now towards 4. We might at this point turn our flow up a little bit because we're adjusting the regulator under load. And we very carefully approach 4 and put it right on the line. So we now have oxygen. I'll just turn that down a little bit. The next thing to do is to check our nitrous supply pressure is correct. So what I'm going to do is turn the nitrous oxide cylinder on. And the flow meter is actually running. And looking at this one, it's way too high. It's approaching 600. Now that won't hurt the machine, but it means the machine is not operating optimally. Now that's interesting because we're going to have to now lower the pressure. Now lowering the pressure on a regulator has to be done in the correct manner. Because of the way the adjustment screw in here works, we want to take out any mechanical backlash from the system. We do that by adjusting pressures up. So in order to do a proper adjustment on a regulator, we need to have gas flowing through it, and then we're going to lower the pressure. And you can do this quickly. So I've taken it down around 200. Now slowly I'm increasing pressure. And I'm adjusting it, I'm increasing it slowly because we want the regulator to be working as it's losing a little bit of flow through here. And we put that right on, jumped a little bit, but that is in fact right on 400 now. So, from this exercise we've determined that our supply pressures are in fact correct for running the machine. Okay, I'll just move these cylinders around the back so they're out of the way. Now there's one test that I want to do, and that is verify that when the oxygen supply is turned off, 2 things should happen. We should get an alarm as the pressure falls, and we can see it's falling here. We should get an alarm, and also our nitrous oxide bobbin should drop. Alarm, and our nitrous oxide has been shut off. So that alarm should stop, and also this is gradually changing across to red. Now we have checked there, the alarm system works at low pressure. We kind of knew that already, but the alarm system is working on low pressure. Our visual system is working, and most importantly, without oxygen, the nitrous oxide flow is stopped. It's important to know the fundamental operating design of a machine, and you can quickly verify it. The other thing we want to check is, can we administer we can't at the moment turn up nitrous oxide because it's shut off. But the next thing to determine is, can we administer nitrous oxide on its own. Turning the oxygen back on. Most machines make that noise when the oxygen's first turned on. It verifies that the alarm system's working. So that's good. Now what I'm going to do is I've got a fairly high flow of nitrous oxide set there now. I'm going to turn the oxygen flow off and see what happens. So, this is interesting. You see there that as we're lowering our flow of oxygen, the nitric oxide flow is following it. Now what that's telling me is that when we've got our oxygen set to minimum flow, we can't increase nitrous oxide. This machine is fitted with what's called an anti-hypoxic device. So we can test that by opening up our nitrous, opening up oxygen, setting a 1 litre per minute flow here, and it's a little bit above 3. So it's a 1:3 ratio. Now this will not administer more than, less than 25% oxygen concentration. And that's what we want to see on a machine. Now, that's as it would work in our context. In Australia and New Zealand, where we have good quality oxygen supplies and good quality medical gas, we can trust that because of our supply chain. It's so good. If you're working in other countries, however, oxygen might not necessarily be 100% oxygen. We manufacture our oxygen by fractionating air, making liquid air, and then fractionating it off through a process of we take the different cuts of gas off. So when we talk about 100% oxygen in Australia and New Zealand, that's exactly what we get. There are other means of measuring oxygen, of manufacturing oxygen, which involve oxygen concentration. And depending on the quality of that plant, the oxygen concentration may vary. And a good friend of mine, Robert, who's done a lot of travelling in Africa, has measured oxygen in cylinders as low as 60%. So while this might be all well and good to use and nice and safe in our context, when your oxygen supply is questionable, you really need to measure what concentration it is. And the only way to do that is with an oxygen analyzer. Doesn't have to be medical grade. That's just a license to print money. The ones you get at dive shops are perfectly okay. So my advice, if you're going overseas and you're to a country that doesn't have a known supply chain of oxygen, taking an oxygen analyzer is advisable, highly advisable. So we move on. We've now satisfied to this point. Now we have to test the rest of the machine. And the way we do that, we set a minimum flow of oxygen of around, well, this will only go to 1/2 litre. So that's what we're going to test against, 1/2 litre. And this is where our pressure gauge comes in. What we're going to do is place the pressure gauge on the common gas outlet. And of course, this being blocked, we will see a pressure increase. If that pressure increase went above about 35 millimetres of mercury, I would be happy that we've got a good tight seal on our system. Now, the way we do that is simply push it on. But we've got to be aware that this machine may not have an overpressure relief valve built into it, and we could destroy this gauge. And that's why we keep our flows low, because it gives us time. The other thing is, when you're testing a machine, you never touch the big red button. This is the flush button. It will administer a 40-litre flow out through the common gas outlet. It will destroy this in a matter of milliseconds. So never ever touch the flush button. And just be aware of it, because this one is recessed, some of them aren't. They've got a proud end on them. So here we go. Our pressure is increasing. That's good. It's gone past 40. I just want to see how high it will go. Oh, look, 60 millimetres of mercury pressure, no problem. And it looks like it'll keep going. Now, we've verified two things from that we have a good seal on our machine to this point, and also that we do not have any pressure limitation built into the machine. So that's information. That's information that we need to know about. The other thing is testing the seals in this at these 2 points. Without a vaporiser in place, we want to verify that these seals are working. And the way we do that is very simple. We have some pressure building up in the system. We push down on that, release the pressure, and let go. So that's a little tiny self-sealing valve there. So that one was good. Same with this, push it down, let it go. So we verified that the seals in here are in good condition. Now what we're going to do is mount our vaporiser. Oh, the other thing we should have done is had a quick look at those O-rings. The O-rings are here, they're fully intact and they're nice and soft. These are a little softer than normal industrial O-rings. However, if they had to be replaced with industrial O-rings, they will work. We place the vaporiser and we lock it on. And it's always a good idea just to give it a little bit of a shake, just to make sure that it's fully seated. Now what we're going to do with the vaporiser off, we're going to check the pressure. And that's good. We've got pressure increase. So we know that the seal behind the vaporiser is working. And then we're going to turn the vaporiser on, and we're going to look for the same response. And yes, it's rising. So we're sure now that we've got a good seal on the vaporiser, and also that the internal mechanism of the vaporiser is sealed as well. If this did not rise properly, the first thing to check are the fillers to make sure that they're tight. All of the filler caps have a mechanical seal on them, and that needs to be intact. And also just make sure that somebody hasn't tightened the cap on and cross-threaded it. It might appear to be tight, but it's not actually making a seal. Okay, and if there was another vaporiser here, we would do the same with it. We would then place it and check it. Now we're ready to move out from here. So we've qualified that the body of the machine is in good condition. Now we're going to move out to the breathing system. We can see from here it's a circle breathing system. It has a CO2 absorber built into it. It has unidirectional valves which control flow in the inspiratory and the expiratory side of the circuit. It has a bag vent switch on it. Patient connections here, inspiratory and expiratory, they're both marked, and also a bag connection. Now at this point, I'm going to discuss this machine and some of its limitations when oxygen supplies are low. It's designed to run with a ventilator. Ventilators can consume, at best, 2.5 times minute volume. So if we're ventilating a reasonable sized adult, maybe a minute volume of 5 litres a minute, we're going to lose between 12 and 15 litres a minute just running this, at best. Some ventilators can consume up to 40 litres of oxygen a minute. So when you look at that, while it's a convenient labour-saving tool, and it works well where we've got abundant supplies of oxygen, as we have in Australia and New Zealand, in a remote area, you wouldn't want to use that. And probably, if it's not used as a doorstop, dump it in the lagoon, right? Be great for some coral to build on and for fish to make a home in. So what we might well do later on when we get the machine going is actually remove this. And we'll tidy the machine up as well. So that's my word on ventilators. Ventilators are only suitable in first world countries where oxygen is abundant. And you'll find in most applications in the developing world, people just handbag. They're not doing 12-hour neuro cases. It's all short stuff. Or relatively short surgery. Now, this is the supply hose that connects the two halves together. We're putting it on the common gas outlet. This doesn't have any locking mechanism on it, so we want to make sure that it's firmly attached. And this end here would go to the fresh gas connection on the base of the breathing system. So it's just a snap fit, and there we are. Now what's interesting about this is that this breathing system doesn't have what we call an adjustable pressure limiting valve on it. I've inspected it and it's a bit different. Now, classically, we have a circle breathing system which looks like this, where we have our fresh gas coming in, we have our bag on this side. We have our adjustable pressure limit valve on the other side, our absorber in line here, and the gas basically gets pumped around the circle by the bag being squeezed to force inspiration at the patient, and then when the patient exhales, gas comes back out and gets recollected in the bag. And the adjustable pressure limit valve spills any excess gas we don't need into the scavenging system. Now, we don't have anything that looks like this. However, this diagram is from the GE ACES machine. This is the breathing system of the GE ACES. And what's interesting about it is that here we see the patient circle, because it is a Boyles machine. Here we see the patient circle, our unidirectional valves, our absorber. What's interesting, we have a bag vent switch here, and the APL valve is in fact connected in series, effectively in series with the bag. And I'm thinking, looking at this machine, this is the APL valve here. It's marked with the right sort of pressures, and also it can be completely closed, turning it clockwise. That is the APL valve. Our challenge is to make up the circuit in such a way that we install this valve in series with the bag. And looking at it, that's our only option as well, because we must have an APL valve. Okay, so we can start assembling the patient circuit. First thing we'll do is select our breathing circuit. This is a septal circuit. So the inspiratory and expiratory legs of the circuit are both in this tube, and we have an arrangement here whereby we connect to the machine. So we can connect those up. So one on expiratory, one on inspiratory. We have a bag on here, which we can take off, but that's going to be our patient connection. The next thing we need is the bag connection. Now, looking along here, we have our bag, and we want to put that in series with this. And that's fortunate, we have an adapter on here. And ergonomically, it's probably better it points this way. So we'll connect this bag up to this side of the APL valve. The next thing we're going to need to do, if we're connecting it in series with the bag, is we'll need to have a connection from this point on the APL valve to the marked bag connection on here. I'll just have a look through here. We could use this hose, but in my experience, this is not good stuff. It can crack, very prone to leaks. So I'll discard that. This one looks to be a better option. It looks to be made to the same standard as that hose. So that's going to go on the back of the APL valve and then around and hook onto the bag connection here. Now I'm pretty confident that we've got that connected properly. And while I haven't tested it yet, I'll just make sure that our configuration will work. So what I'm going to do now is just hit the flush button. If our configuration is correct, and I've got the APL valve closed, both these bags should inflate when I push the flush button. But certainly they are. I'll just get a bit closer. We're hearing an escape of gas from this. Now that indicates a leak somewhere. might have found what the reason is. There's a sampling port on here. And we're going to have to block that some way. Now it looks to be a lure connection, like a medical lure connection. Ideally, I'd just go to the anaesthetic storeroom and get a bung. Screw it on there. But we haven't got that. So what we can do is improvise, and often this is what you have to do when you're out in the real world, is improvise. So it's a bit of hose. We could possibly try putting that on there. No, that's not going to work. That looks like it might. It slipped over that nicely and it's making a seal on the back end of it. And we can just clip it off with artery forceps, or we could maybe get a cigarette lighter and melt it and squeeze it together. It'd make a seal that way. These are the sorts of things you have to do. You have to be creative. Now, have we done the job? We'll find out. Pressurise the bags again. No, can't hear anything, so we've sealed it off. That doesn't look real pretty. We'll have a bit of a look around and see if we can get something a bit better. But remember, we're just testing this machine at this point. Good. Now what we need to do is determine whether this is leak-free. The way we do that, this is our bag, this is our patient connection. The simplest way to do that is to connect our test gauge up to the circuit. We can let that fall. Connect our test gauge up to the circuit. Now, once again, we've got a gauge connected. Instinct would be to push the flush button. Not a good idea. I'm just going to increase the oxygen flow, so it'll take a little while to blow that bag up, but we've got things under control. This is good. Pressure's increasing. Okay, turn the flow right down. We're not seeing any change in the size of the bag here, and we're holding 30 millimetres of mercury pressure. So, in one go, by placing the test gauge here, we've tested the integrity of the whole patient circuit and the bag limb. This is not an uncommon way of testing a machine. And it's all just done with this one simple piece of test kit. So, pretty good. We've got our, we know our APL valve is sealing. We know we've got a good tight circuit with no leaks. The next thing we're going to do is determine whether these unidirectional valves are working. The way we do that is we can now use our flush button, fill the circuit with some gas. That's good enough. The unidirectional valves here are critical to the operation of the system. As we squeeze the bag, we should see the one on the inspiratory open. And when we squeeze the patient end, we should see the other one open. And from visual observation, they're working fine. It's vital you check these. One may be stuck, closed, or worse still, stuck open. The danger of it being stuck open is it will still get the tactile feel of this. But what's happening if the valve is open is that gas is just shuttling backwards and forwards along one length of tube. It's not actually going around the circle. CO2 is not being removed, and eventually the patient will suffocate. So being able to verify that these valves are working is vital, absolutely vital. Now, the fact that we've got a pressurised circuit and it's sealed is an opportunity to test our APL valve. When I open this valve, we should hear a release of gas from the system. Yes. So, there we are. We can squeeze all gas out of those two bags. So we know our APL valve's working. This is really good. So in that condition, we've now got a usable machine. One of the things I have observed is that there's a patient pressure gauge here. Now, it would be really, really good if we can connect this into the circle somehow. And just looking at the machine, under here, there's a hose. It's quite short, so I would assume that that's the connection to the pressure gauge. Assume. And also the fact that it's got a 20 millimetre female, 22 millimetre female, and 22 millimetre male. It's an extension, effectively. Now, just to go back to the diagram I showed you of the ACES machine, here's where they sense patient circuit pressure, and it's quite close to the inspiratory side of the machine. So that's probably a guide that we could do this to this machine. So we'll find the connection marked inspiratory. Here it is here. We'll take this out, put that in, and we'll find out whether this hose in fact does connect to that. If it doesn't, we can take it out. Nothing to lose. This is all icing now. So once again, I'll pressurise the system. Close the APL valve will help. Pressurise the system, and look, our pressure gauge is going up. And we can see that there. We can see that movement in pressure as I squeeze the bags. It would also be an opportunity too to check the calibration of the APL valve. So at minimum, it's very close to zero with it fully open, and it looks like we can go anywhere in between. So that's good. So we've verified that our APL valve in fact works, and we've now got a means of monitoring patient pressure. If we were really keen and we knew this was a good gauge, we could actually verify the accuracy of this gauge, because 1.36 times millimetres of mercury equals centimetres of water. So, we've come from the beginning of the system with our gas supplies, adjusting our regulator, to testing the gas delivery system and its inbuilt safety systems. We've come through the back bar, checked the seals on our mount, and finally checked the seals inside the vaporiser, out to our common gas outlet. We've got information that the machine is completely tight, it's good and well sealed. We found out that it doesn't have a pressure limit valve built into the machine. We've then come out and we've assembled and fully tested our circle system. Now, at some point, we're going to have to be able to change the soda line here. So it would be a good idea to verify that this canister will come off and the means by which it comes off. Now, looking at this, there appears to be some sort of release clip. Ah, right. So that comes off. And it looks just like a food storage container, really, with a couple of clips on it. So the way this would be emptied is it would just dumped and refilled with soda lime. The biggest problem with any sort of absorber that uses granulated material is that the granulated material can get caught under the seal. So when you're filling these things, make sure that the seal is wiped free of any dust and the mating surfaces are clean before you clip it together. The other thing is, when you're handling it, don't shake it too much because we don't want any dust to be liberated from the stuff. And we'll just reassemble it, and looking at it, it would appear that it doesn't matter which way round this thing goes. It hooks under that, and one would presume that when we push that down, it locks on. So that's something you need to know. Soda lime may be of variable quality when you're working in remote areas. The soda lime that we use in Australia and New Zealand has a dye indicator in it. It'll either start at a colour and go white, or it will be white and develop a colour as it gets consumed. Most of them start white and go to a colour, but don't assume that. The best way to know that your soda lime absorber is working when it's connected to a patient is it will feel warm, because the soda lime breakdown process is exothermic, so that should feel quite warm. The reason that we use Boyles machines classically is that you can get away with administering pretty much oxygen down to the physiological demand of the patient. So they're very frugal on the amount of gas that they use, medical gas. And the other thing is, because we circulate the gas around in a circle and we only take out the dangerous stuff, the CO2, the amount of volatile agent that we use is limited as well. So in a country where there is a good, reliable supply of soda lime, they work well. But here we are. We've basically got this. I think we'll then proceed and we'll strip the machine of this ventilator. I've not taken it off, so I don't know how it comes off. First thing we'll do is disconnect the oxygen line anyway. Looks like it's a push connection. Yep, okay, so at least first thing we've done is disconnect that. That's loose, that's loose. Okay. So what we've done here, we've taken the ventilator off. It makes the machine look tidier. As we speak, it's being taken out by canoe and dumped in the lagoon. Everything else is pretty tidy. Oh, there is an air connection here. They don't have medical air. So what I would recommend is that that's taken off and probably put somewhere away from the machine. In this case, we'll just put it in the drawer. Limit the opportunity for things to go wrong. They only have nitrous oxide and oxygen where we are. The other thing we might do is turn the air flow meter off. And pretty much we're happy to use this machine now. So I hope that has been instructional. What you are used to seeing could be different to what you encounter, but by applying some basic principles of common sense approach, a little bit of knowledge of how to set pressure regulators, how to test a machine, how to make one of these and pack it, take it with you, you can do some very good stuff. And the only tools that we used were an Allen key, pressure gauge, and a little bit of creativity using an artery forceps. Thank you.